Now we know when we have two objects that are at different temperatures, so when there's a temperature difference between those two, there can be an exchange of energy so that they can come to the same temperature. This is what happens like when you put a piece of ice in your glass of water, right? They come to an equilibrium. So thermal equilibrium is when things get to the same temperature. Okay, so that's not a surprise. This transfer that happens between two objects due to a difference in temperature. So if I have something that is temperature 1 and another something else that's at a second temperature, and we bring them together and we have this change so that the temperatures by the end, here's 1 and 2, they come to some T final where they're in equilibrium, then this exchange of energy is called heat. That's what heat is. It's this transfer of energy. So if this is warmer, so if this is higher, so this is the high temperature, and this is lower, then what happens is we have, as these come together, we have heat exchange, heat going from 1 to 2, heat energy that travels from 1 to 2. In this case, the way I've shown it, it would be through something called conduction, probably is the most common way. So our letter for heat is Q. So Q is heat. Yeah, I know Q is not in the letters for heat. I guess it's just the letter that we ended up with. And this is, heat is really energy that's transferred due to a difference in temperature. And it's measured in joules. And it took some time historically to really make this connection between heat and work, because for a long time people thought these were different things, but these actually are. So we'll measure these in joules. You may be more used to measuring them in what we would call kilocalories. This is what is printed as just calories on your food. Okay, so if you know something is 100 calories, that's what it's really measuring, kilocalories, which we can convert to joules. Okay, so how does this work? Well, when we have a solid, we can talk about the amount of heat needed to increase the temperature. So we say the amount of heat that's needed to change the temperature, the amount of heat that's needed to change the temperature depends on the mass. So this is the mass, this is measured in kilograms, and some constant, and this constant is called the specific heat. And what it does is it tells you how hard it is to change the temperature. So if you get some heat transferred into material, how much temperature change does that cause? Obviously, if you have a big barrel of water, that takes a different amount of energy than if you have a cup of water to change its temperature 3 or 4 degrees Celsius. So specific heat, you can again figure out the units because this is going to be in joules. This is in, it's going to be in Kelvin or degrees Celsius because we have this difference here. So if we just look at the units, we need this times this times this to give me joules. So that means my specific heat, the units of my specific heat, had better be in joules. So I have that left, divided by kilogram Kelvin or joules kilogram degrees centigrade. Okay? So that's the specific heat. So that tells us, that's a way to measure how hard or easy it is to change the temperature of something. Okay, just for numbers, specific heat of water, you may be used to seeing it as 1 kilocalorie per kilogram degrees Celsius or 1 calorie per gram as the specific heat of water, if you've seen this in chemistry. In our units where we're looking at joules, the specific heat of water is going to be 4,100 and I have to look, 86 joules per kilogram. I'm going to be using degrees Celsius for the most part. Okay, the specific heat of ice, it actually takes less energy to increase ice by 1 or 2 degrees than it does the same amount of water, because this is about 2090 joules per kilogram degree Celsius. So we can change the temperature of things by having something warm next to something cooler, the heat transfer. We can also do it by doing work, right? So a way that that's done, for example, in water is you have water and you stir it, okay? And so that work that went in, the mechanical work of stirring it, can go into water. So there are lots of different ways, and you know of other ways as well. But I just want to sort of lay out how this is set up. And when we look at two objects like this that come into contact, then this heat flow from one that goes into two, we must have conservation if it's an insulated system. We can't suddenly say there's a magical amount of heat somewhere that either disappears or is added into the system. So that when we have an isolated system, so an isolated or an insulated system, like this is sort of isolated from everything else, then we would say the heat from one must go into the heat of two, so that altogether these are 0, right? Because one is going to be, if one is going from high to low, in this case, T1 is going from high to low. This is going to be somewhere in the middle. Not exactly in the middle, unless these are exactly the same mass or the right numbers for the specific heat, but somewhere in the middle where we have this Q1 would be losing energy, right? Q1 would have T final less than T initial, so it loses, it has a loss of heat, so that would be negative, right? Yeah, I've got room. Whereas in this example here, for the second object, I guess I should say this is of T1, T final is greater than T2, so it's greater than the initial. So according to this equation, remembering of course that this is T final minus T initial, that this would be positive. So we have a positive and a negative, and they have to equal 0. And that's a way we can actually find out what our middle equilibrium temperature is, right? So if we start with a cup of water that's boiling or just at boiling, so 100 C, and we start with some water at room temperature, call it 20 C, we can figure out sort of, if this is a cup and this is a half cup, where we end up in the middle, okay, just by setting up these equations.